and also the direction. Average acceleration, also same definition. It is the difference in velocity, the final minus the initial, then you divide by the total time taken. Okay, that's the average. Instantaneous is you go and do a differentiation of the velocity. Okay, so the definition for 1D, whatever we have learned in 1D, actually it is the same definition. Okay, so let's look at some the illustrations here. So imagine this curved line, right? This is the particle that's moving along this circular line, right? So at a certain point, you are at P1. Later, after some time, you reach P2. Okay, this is a circle. So at P1, the velocity that you have, right, is actually a tangent to that path. You are moving in a curve, right? Tangent, that means is the mathematical definition of tangent. So tangent to that path. Okay, means you draw a straight line at the path. That's V1, and that's the direction. At that instant, it is moving at that direction. Okay, but later, after a while, when it's at P2, if you draw another tangent, it's currently moving in another direction already. So it's facing here. So in other words, if you move in something like a circle, right, you are always changing direction, the velocity, which makes sense, right? You are always changing direction. Okay, so following this, V2 is here, V1 is here. If you want to find the average acceleration, you follow this definition, right? It will be taking V2 minus V1 and then divide by the total time taken. So if you take V2 minus V1, right, these are vectors. If you take V2 minus V1, you are going to get a resultant like this. V2 is like that, right? V1 is here. So if you do a V2 minus V1, that means that you take a V2, then you add a negative direction of V1. Okay, you're going to get a resultant that looks like this. So this resultant, right, you realize it is at first not so intuitive, like it points in a direction that is totally off, right? One, you are going here, after that you are going here, but actually you're accelerating towards the other side. Okay, so it follows the definition. This is correct. Okay, so you will be accelerating elsewhere, just that may not be so intuitive now. But after that, we will see that actually when you move in circles, right, your acceleration is towards the middle of the circle. Okay, but vector-wise, this is how we do it. Any questions so far? Okay, don't have, good. So 2D motion with constant acceleration, again, down here we have some derivations to show how the equations are valid for 2D motion. But I don't want to confuse you all so much with the derivation. So just very, very roughly again, down here, since A is constant, A must be constant again. We have this equation here. This dv over dt is our acceleration, is constant. And then in another direction, right, because now 2D, after we have x, we also do the same thing for y, which is also must be a constant for this to be valid. Then we go and integrate both. We will get this equation. Actually, they are all in this same form. Okay, v equals to u plus at. They are all in the same form. Then this slide is to say actually the equations are the same also. Okay, when you apply in two directions, you see you have an I and a J coming out. That means one in the X direction, one in the Y direction. You do them separately, right? They are all going to be in the same form as whatever we have derived. Okay, so in the X direction, you're going to have this. This is the same as S equals to UT plus half AT squared. You see the Y direction is also S equals to UT plus half AT squared. So independently, right, they will also have the same equations, just that they are applied in different directions. Okay, so whatever that we see in the previous two slides, right, actually it means this, okay, this sentence inside here. So for 2D motion with constant acceleration, it is equivalent to two independent motions in the x and y directions with these constant accelerations. So when you have 2D motions, you have one x and one y, correct? But if you analyze them separately, like for example, you take a look at the x direction first, you can apply the equations. Then if you go and isolate the y direction only, right, you also can apply the four equations. So that's what this previous two slide is trying to say. And this concept, right, we'll be using to solve 2D motion. Okay, so we will analyze in one direction first, find some info, then use the new info in another direction to find more info. Okay, something like that. So a very standard kind of 2D motion, the most basic one, right, is a projectile motion. So what is a projectile motion? Is when you throw something in a direction, and because gravity is acting, right, it will still move in a direction but come down. Okay, so for example, a cannon you shoot, it will come down. Basketball you throw is actually a projectile motion. This one is, I think, long time ago, a lot of people play this game, right? This is heavily based on projectile motion also. Okay, so in our study, for this case, assumptions for projectile motion, we assume free fall acceleration. So at any time, right, let's say we were to shoot a particle upwards. That means initial velocity in this direction at a certain angle counting from the x-axis. Okay, so at any time, you are going to experience free fall acceleration throughout. And we also neglect air resistance. So in real life, you throw a ball, right? You are going to experience air resistance because we are flying through air at very fast speeds, right? The air will try to slow it down. But for the most basic case when we are studying, right, we neglect that. That means it's like a perfect projectile motion with nothing trying to slow it down. We also choose y direction as positive upward. That's what we are plotting here. So y upwards. In this case, right, the acceleration in the x direction will be 0. And then acceleration in the y direction will be minus g. So these two things, right, is a very standard thing for projectile motion. Very standard criteria. So in the y direction, okay, if you look at the y direction only, there will always be this g trying to pull it down, correct? So if you analyze y direction, the a will always be minus g. In this case, y upwards, right? So there will always be a minus g acceleration. Ax equals to 0 down here. That means if we are looking at motion in the x direction only, right? The motion along the x direction, there will be nothing trying to speed up or slow it down. Okay, that means if you were to isolate the x direction, let's say you throw something like that, let's say you throw something like that, if you are to isolate the x direction only, this direction, if the ball is moving like that, and then if you imagine there is a projection of the ball along the x direction, right, this x direction will always be moving at the same speed until we hit something and stop, of course. Okay, so that is what we meant by x acceleration equals to 0. It's not speeding or slowing down. And then for this particular case, x naught equals to y naught equals to 0 and t equals to 0. This is trying to set some boundaries for this thing we are trying to illustrate. So it's trying to say that at time equals to 0, that means at the start, we take the x naught and y naught to be 0. That means it will start from the origin. And initial velocity v naught makes an angle a naught, alpha naught with the horizontal. So you shoot up here, v naught velocity, alpha naught. Okay, so this is the projectile motion that we are looking at. So just now you were looking at this part, right? This projectile motion will move something like this. Following the blue line. So you see at any time, right? So these dots, they are at different sort of snapshots. Because it's still moving somewhat upward and forward, right? You see this, it can be resolved into the upward direction and the forward direction. Okay, so these are the resultant vectors. That means at this point, this particle is currently moving here. Okay, and then we can resolve into this and this. But later on, when you reach the top, right, there's no more up and down velocity already. At that moment, it's like it's not moving in terms of y direction. It is staying there, like a dropping from free fall like that. The only velocity that it has is to go forward. Okay, so at here, the resultant velocity is just the x velocity, it's the same thing. Then after that, when it's going down, same thing. If you have a vector pointing here, you can resolve it to one x direction and the other one in a y direction. Okay, and so on. So these are just 5 different snapshots. Then this part here is derived from the very initial throw, right at the start. Okay, so you see this v naught x, that means the velocity, the initial velocity in the x direction, v naught x, is equals to v naught, which is this one, cosine alpha naught. V naught is the hypotenuse. If you want to find this one, right, you will just take the hypotenuse cosine alpha naught. Okay, this is your trigo, same thing from your trigo. Because you see, cosine alpha naught is equals to what? Is equals to this one over this one, right? Adjacent over hypotenuse. So if you want to find adjacent, it's actually just hypotenuse multiplied by cosine alpha naught. So you get v naught x. Then same thing for v naught y. Usually if x is cosine, y will be sine. Usually it's like that. Okay, because it's a trigo, it's a triangle. It's a triangle. Okay, so following the trigo, you are going to get this. So we are just writing in terms of the initial velocity. So from that, we can see that the velocity equals to v naught x, which is, this is we derived just now, right? It is actually a constant. Because remember, we say in the x direction, the velocity throughout will not change. Okay, so the velocity throughout is just a constant. It will be this value, okay, until it stops, until it hits something. And then in the y direction, so for 2D motion, right, we will usually look at one direction and then the other direction separately. So for the y direction, if you apply v equals to u plus at, or v equals to v naught plus at, you are going to get this expression. Basically, it's just that, then you sub minus g inside. And then is the v naught y we have already found in the previous slide, right, from the starting position. So you put here. Same thing for displacement, you'll be using this equation. This is the same as s equals to ut plus half at squared. Okay, then we put in this s equals to ut, this is ut, then the half at squared disappear. Why disappear? Because remember, acceleration in the x direction is 0. Okay, in the x direction, we don't accelerate at all. Okay, that's why disappear. You are left with only one term with it, which is this one. Then in the y direction, same thing. You use the same equation, s equals to ut plus half at squared. That a, right, just change to minus g. Okay, so these are general equations for this particular case of projectile motion following this axis. Okay. Projectile motion is a superposition of two motions, one constant horizontal velocity, which is the part where the x don't change the velocity, and then the other part, right, is vertical free fall. Okay, so if we analyze like that, right, there is free fall. If you analyze like that, you will know that the velocity don't change. So another concept question for you all to think about. Place 2 tennis balls at the edge of a tabletop down here. Sharply snap one ball horizontally off the table with one hand while gently tapping the second ball with your other hand. Which ball will fall to the ground first? Explain your answer. So basically you have a ball here. Let's say you push it horizontally outwards. One harder than the other. So one will go further, right? Then one will drop right in front. Which will fall to the ground first? So I'll take a minute to think about it. It's also a projectile motion, right? Okay, who think this one will reach the ground first? Who think this one will reach the ground first? Who think same time? Okay, good. One student thinks same time. So the answer is same time. Okay, correct. Same time. Why? Why is it same time? Because if you see down here, you are starting from the same height, correct? Starting from the same height. You don't need to care about the x direction. You just need to look at the y direction. They are starting from the same height. So now it's as if in the y direction, when you analyze the y direction, you are dropping something from free fall. Okay? You are dropping something from free fall. So they start at the same height, they are going to travel the same distance with the same acceleration, which is gravitational acceleration. They will both reach here at the same time. Okay, so they will reach at the same time. Okay, oh, okay. Okay, good. Then we continue. Now we talk about some other properties of a projectile motion. So we have this thing called the trajectory. That means the path taken by the projectile motion. So if you want to find a path taken, right, we will go back to the equations and then try to change the equations to suit our form. So for trajectory, if you want to plot out the path, right, what do you need at the end? You need y and x, right? Y in terms of x, then you try to plot out on the graph. So we will use these equations and then try to eliminate t from these equations. So end up, right, we are going to have an equation with y equals to something x. Okay, may not look so simple, but you know y equals to something x. When you plot on a graph, it will give you some shape, right? That shape that we see is actually the path taken, which we call it the trajectory. Okay, so you see, if you compare to this is actually a parabola. That means something x minus bx squared. So you see down here, right, there's a minus x squared. You will know what the graph will look like, right? The shape. You look like a set face, which is correct, correct? Because projectile motion, it will look like a set face shape. Okay, so this describes the trajectory. Also, for a projectile motion, there will be a point where you reach the maximum height. That means in terms of the y direction, you will reach the largest value. Correct? So that one also can be found by substituting the right conditions inside. So at the peak of its trajectory in the vertical direction, that point, right, Vy will be 0. Make sense? When you reach the maximum height, if you look at the vertical direction only, the velocity there is as if it's 0. So if you look at the y direction, the ball will look like this. From the bottom, go to the top, then come back down. So when you're at the top, right, Vy equals to 0. Okay, so that's the condition we will want to put in to the equation to find further info. Okay, so that's the condition. So if you put in into this equation, this is our v equals to u plus at for the y direction. From here, you will be able to find an expression for the time taken. So here you have the time taken to reach the peak. Time taken to reach the peak. Then you use this to put into another equation with distance. Okay, in this case, this is our s equals to ut plus half at squared for the y direction. Okay, when you put in, you are going to get a value, which is a distance, right? That value will be your maximum height because we already set this criteria at the start. Okay, because we already set this criteria at the start. So this h that you get here, or rather this y value after doing that, will be your maximum height. Okay, so the maximum height you see, it will depend on your initial velocity. Of course, right, if your initial velocity is higher, you try to throw at a certain angle, you throw it faster, you will reach a higher height, correct? A larger value. It also depends on the angle that you try to throw the ball. So that's the height. We also can find the horizontal range. When we say range, right, we mean in the x direction, what is the furthest it can go? That is the range. Okay, that's the range. This is the height. So we're going to set some criteria to find the range. When the projectile reaches the ground, y will be 0, correct? Remember this equation, this is the trajectory, right, which is set phase just now. So the criteria to know the range, right, is you can set this y equals to 0. Because when you throw something, when it goes to the other side, what happens? The y go back to 0, correct, when it hits the ground. So that one is a criteria to find where it exactly can go. Okay, so if you set that as a criteria, you will be able to find the range. And from this equation, something interesting that you can see from this equation is there's a sine 2 alpha naught here. This alpha naught is the angle that you throw, right? It's the angle that you throw. So this R is a maximum value when this is 90 degrees, correct? Because you know sine 0 is 0, sine 90 degrees is 1, right? A sine curve, it varies like that. So the maximum occurs where this sine value is 0. So if you see 2 alpha naught here, right, the max value will occur at 45 degrees. When you throw it at an angle where alpha is to 45 degrees, you are going to get the furthest range. So to illustrate it on a graph, right, it will look something like this. If you throw it without air resistance, if you throw it at a 45 degree, you are going to get the furthest range. Okay, if you throw it too high at a very large angle, you're going to end up closer. Same thing for the very small angle. Okay, any questions so far? You don't have, good. Another concept question for you all to think about. A battleship simultaneously fires 2 shells at enemy ships. If the shells follow the parabolic trajectories shown, which ship gets hit first? Who thinks it's A, B, C? Okay, what's the other thing is C? D, E? Of course, D is wrong. Okay, so which ship gets hit first? B will get hit first. Okay, B will get hit first. Because you see which one reached the highest peak. Okay, this one will take a very long time to go up and come back down if you analyze the y direction only. Okay, if you analyze the y direction only, this one reached lower peak. So it's going to reach first. So same thing, if you take the very extreme case, right? One ship is here. Then one ship is very far away. This one is here. Let's say you go and shoot up like that, then come down. Compared to one ship, you go and shoot like that. This one is going to hit first, okay? The further one is going to hit first. Okay, so let's go to one example. In a detective story, a body is found 5 meters from the base of the building and beneath an open window 26 meters above. Would you have guessed the death to be accidental and why? So something like this, right, is actually a projectile motion, something that is thrown. So they will have some x velocity, you also have some y velocity, right? So this is the way to solve it. Time taken for the fall, assuming 0 initial vertical speed. That means for the y axis, right, we assume it starts from free fall, starts from rest. So you are going to get something like that. this is from your s equals to ut plus half at squared. Again, same thing, the ut becomes 0. So you see, after a while, right, actually, the things become quite standard one. Like when you start from rest, then the u will become 0. Okay, so y, you will be left with minus half gt squared. Down here, if you put the values inside, you know the height that is going to fall. G, of course, you know already. You will be able to find t, which is the time taken for the fall. In other words, if you drop something from here, right, no matter what the x velocity is, but if you look at the y velocity only, you know that it's going to take 2.3 seconds to reach the ground. Then you use this new info to calculate the horizontal speed. This question a bit vague, they never ask you to calculate speed. Okay, this is just in the exam, right, you won't have questions that are so vague. Okay, they will ask you to calculate exactly what they want you to find. They won't ask you, would you have guessed the depth to be accidental? Okay, this is just for example. But let's say if they ask you, imagine they ask you to calculate the horizontal speed. Okay, what is the horizontal speed? That means this is the way to do it. Okay, so you'll find out that it is 2.2 meters per second. Okay, and to answer this question, could it be accidental? If it's accidental, right, you expect the horizontal velocity to be close to 0. That means you accidentally fall down, right? The x direction should not have much velocity. And he should be much closer to the building. But in this case, if you compare to our normal walking speed, right? Our normal walking speed is 4 km per hour. This is thrown off at much larger speed than this one, 7.8, okay, which is twice our normal walking speed. So if that is the initial, that is how he is getting out of the window, right? He must have jumped off or someone threw him down. It cannot be just dropped down. If not, he won't fly so far. Okay, so this is 2D kinematics. Any questions so far? No, definitely not. So this is just an example, like interesting example to show. So if this happened to be a question, right? Of course, it won't be so easy like 2 steps like that, of course not. But if you're going to get a question like that, they will ask you something very clear, like calculate the horizontal speed, like that. They will ask you to calculate that. They won't ask you, would you have guessed the depth to be accidental? This is too vague. Okay, so this is just something interesting for y'all to think about. Okay, good. Any other questions? Yeah. Okay, why is the 26 negative? Okay, one of your classmates asked why is the 26 negative? So this question, right, if you look at the solutions, the A, right, becomes minus G. So what does it tell you? It tells you that they are taking upwards to be positive. Wait, what happened? They are taking upwards they're taking outwards to be positive. So if they take upwards to be positive, that's why the A becomes minus G, correct? But if you take upwards to be positive, you are starting from here, and then you are going down. What should happen to the displacement? It should go into a negative value, correct? It starts from 0. If you go up, you're positive, but now you are going down, right? You are going down, so you will have a negative value. So it all depends on your choice of axis. Okay, if you choose downward positive, right, the numbers won't look like that, but end up you should get the same answer also. Okay? Okay, good. Yeah, any other questions? Okay, if not, then we move on. Yeah, we move on. So now we move into circular motion, which is also called curvilinear motion. Just now it's rectilinear. That means straight lines. Okay, it could be 2D by straight lines. Curvilinear means you move in curves. Okay, like circle. Circle is a curve. So these are just illustrations of what is circular motion. Ferris wheel, you are moving in circles. If you drive right, if you are here and you turn right, the moment you turn right, you're actually going in curvilinear motion. Okay, you don't have to go in a full circle. If you're at a junction, you try to turn right, or if you are in the second lane, you try to go to the first lane, right? At that moment, you have a curve. You are getting in a curve. Okay, and if you have a pendulum, you go in circles, it's also curvilinear. This is satellites moving around our Earth. That's also curvilinear. And this will be the last topic that we'll be doing, which is lesson 6, in our 6th lecture. So acceleration occurs when there is a change in magnitude and or direction of velocity. So if you change the velocity, right, there will be acceleration, right? That's the definition of acceleration, change in velocity. So this is our recall from last lecture. Change in velocity over change in time, that's our acceleration. And uniform circular motion occurs when there is a change of direction of velocity only. The object moves at constant speed. So when we talk about uniform circular motion, we are talking about an object traveling in circles, but the object is not speeding up or slowing down. It's like moving around the circle, right, at constant speed. Not constant velocity, because direction always change. So if you say moving around at constant velocity, technically something is wrong with the statement. Okay, but uniform, when we say uniform, right, means it's going at constant speed. The magnitude stays the same. So you all can guess that if we say non-uniform, right, that means you are moving in circles, but you are also speeding or slowing down. Okay, that's non-uniform. But we'll talk about uniform first. So acceleration, centripetal acceleration, this term, right, centripetal acceleration, this is the acceleration that we experience while in circular motion. Okay, so if you move around in circles, but you are not speeding or slowing down, right, you will still have acceleration because your velocity is changing. Okay, and this is the acceleration that we are talking about. It is perpendicular to the tangential velocity. So if you move like that, right, in circles, at this point or at any point, your velocity is always tangential to the circle. But your centripetal acceleration will always point towards the center of the circle. Okay, that's our centripetal acceleration. And we also have different ways of saying it. Sometimes we call it the radial acceleration. Sometimes we call it the normal acceleration. So it depends, but they are all referring to the same thing. So if you see like A radial like that, right, means talking about centripetal acceleration is the same thing. If you see like A, then N is below, right? For example, A, then N is below. Okay, we are also talking about centripetal acceleration because we are taking a reference to T. T means tangential. Okay, so this is tangential direction, right? This is the radial direction. So this is tangential and this is normal. So these are just different terms that you need to know. Let's say if the question come out and then got talk about normal acceleration, you all must know that it's talking about centripetal acceleration. It's the same thing. So it's given by this formula, v squared over r. V is the velocity, which is the speed, over the radius. That means the length of the radius. Okay, so this is the formula to calculate this radial acceleration. And r is also called the radius of curvature. Radius of curvature, because you are going in a curve, right? At that moment where your curve is, you will always have this radius if you draw out a circle. Even if you just go in a curve, right? Never complete a circle. Imagine you are turning right at a junction. At any point, right, you can imagine drawing a circle also if you were to complete the circle. So at any point, you will have this radius of curvature, although you never actually continue. Okay, so we can imagine if you only turn very slightly, very, very slightly, right? Your radius of curvature is going to be very large, correct? If you turn very slightly, if you imagine the circle to be complete, it's going to take a super huge round. Correct? If you turn like you U-turn, you lock your wheel, right? Your radius of curvature is going to be very small. Okay, so that is the radius of curvature. And down here we use R, but sometimes we use rho. Okay, rho can also stand for other things like density and stuff like that. But if you understand the concept, right, no matter which textbook or which Google information use what, right, you will know. Okay, so sometimes we use rho to denote this R also. So time for one revolution, which is given by the period T. T stands for period. That means the time taken to go one round will be given by 2 pi r, which is the circumference, divided by v, that's the velocity. Correct, right? You see time taken equals to the distance. Circumference is the distance, distance divided by velocity. Okay, so that's the period. And then if you rewrite it, you can also write in another form. So this is the velocity. Basically, it's the same thing. So centripetal acceleration can therefore be written as, just now this formula is for centripetal acceleration, right? V squared over R. So if you're going to substitute this V inside here, you can find the centripetal acceleration in terms of your period also. Okay, let's say if question give you velocity and radius, of course, very nicely you can find this. But let's say question give you period, don't never give you velocity, then this will be the one that you will be using. Of course, if you want to slowly derive also can. Okay, basically they are the same. They equal each other. So let's look at an example. The position vector of a particle moving in the xy plane is given by r equals to this equation, okay, this expression. R is a vector, is a position vector, where r is in meters and t is in seconds. We'll do one part by one part. So we do part A first. Show that this represents circular motion with radius 2 meters centered at the origin. So how do we show that it's a circular motion? We want to map out the path, right, to show that it's a circle. So from this position vector, something I plus something j, the x, right, the x value is actually this part in front of the I. The y value is the part in front of the j. Okay, so you have the x and you have the y. So how do you show circles? You will refer to the general formula for circles. So remember, the general formula for circles is x squared plus y squared equals to something squared, which is your radius squared. Okay, so if you compare to that, x squared plus y squared, you have your x here, right? Then you have your y here, right? Basically, you go and square this part, and then you square this part. You add together, and then you see what happens. You see whether it ends up as a very nice circle formula. Okay, so just nice, if you go and square this, these two will become square. Cosine square, it will appear here, cosine square. But the other side, just nice, is a sine. So if you do a cosine square plus sine square, what happens? It becomes 1, right? Because cosine square plus sine square equals to 1. Okay, cosine square plus sine square equals to 1. So it will just disappear. And now you have this equation here, which can show that it's actually a circle. Because if you compare to a general equation of a circle, it looks like that. Okay, so like this, you have shown that it's a circle. Then determine the velocity and acceleration vectors as function of time. They give you the position, right? They give you the position. To find the velocity and acceleration, as you all had learned just now, it will be to differentiate this. You differentiate one time, you are going to get the velocity. Then from the velocity, you differentiate one more time, you are going to get the acceleration. Okay? So down here, you will need to know how to differentiate cosine and sine. You will need to know how to differentiate cosine and sine. Okay, but basically, just to briefly go through, if you differentiate cosine, you will turn to minus sine. When you differentiate sine, it becomes cosine. Okay, so you differentiate cosine, right, it turns to become minus sine. But the inside the value, right, you have to bring it out to multiply by the original one outside. Okay, so that's the way to differentiate cosine. Same thing for sine, it turns to cosine, then the inside the value, you have to bring it out to multiply by the outside. So it becomes like this. Okay, so you will get an expression for velocity. Okay, then you will do it one more time, you get the acceleration. Okay, then part C, determine the speed and magnitude of the acceleration. So magnitude is actually just doing your Pythagoras theorem. Magnitude is just doing your Pythagoras theorem. So you see here, for example, V, right? You have something I plus something J. So this is your X and this is your Y, correct? You have your X and your Y. So imagine you have your X and your Y. They ask you to find your magnitude, right? It's just Pythagoras theorem, trying to find the magnitude. Okay? Okay, right? Or basically X squared this is your X squared plus Y squared equals to your something square. So it's with velocity, right? Then it will be velocity squared. So you just finding the magnitude, magnitude. Then part D, they ask you to show that A equals to V squared over R. So this is the equation that we had learned just now. Acceleration, right, will be equals to V squared over R. So from the previous part, V equals to this value, A equals to this value. You just have to go and do V squared, which is you go and square 6, and the R is already given in the question. So if you do it, you'll realize this value equals this one. So for circular motion, the acceleration, right, V squared over R is correct. It's supposed to be correct. Okay, they're asking you to show it. Okay, Daryl asked, one student online asked, all these formulas will be given in the formula sheet. So not all formulas will be given in the formula sheet. There should be a formula sheet uploaded by the course coordinator already. If you go to the system, right, same page as the notes, you will see a formula sheet. It should be uploaded already. Okay, so those formulas in the formula sheet are the formulas that you will see for your exam. Not all will be given. Okay. Part E, show that the acceleration vector always points towards the center of a circle. So from part E, we came out with this equation, right? Acceleration equals to something. Acceleration equals to something. So from question, this is given in a question. They give us the position vector. So if you go and compare these two, right, you'll realize acceleration equals to something negative of the position vector. Okay, means acceleration is always in the opposite direction as a position vector. So you see, let's say we are moving a circle, right? Down here, a position vector, this is point O, right? This is point O. When we say position vector, remember position vector always starts from the origin. So it's from here going out, touching the circle. This is a position vector, correct? So to prove that acceleration point always point towards the center of a circle, you get this, right? A equals to minus 9r. Since r is pointing out of the circle, outside, right? This is r. If you get A equals to minus something of that, is already proving that A is pointing towards the middle of the circle. Okay? Yeah, okay, good. That one is circular motion. Now we come to non-uniform circular motion. So uniform means constant speed. Non-uniform means be another acceleration appearing. So when you move in circle, right, there will always be an acceleration pointing towards middle of circle, right? As we have learned. Now, this particle, right, is also speeding up or slowing down tangentially. That means the speed is always changing. You not just move in circle, but when you move in circle, right, let's say you are driving, you move in circle, you also go and accelerate. That one will be non-uniform circular motion. Okay, so you see, there will be a acceleration coming out. So the velocity, tangential velocity, right, will always change also if you have a non-uniform circular motion. Depends on your tangential acceleration. The part pointing to the middle of the circle, we call that the radial acceleration. The part that is changing the speed, right? The part that is changing the speed, we call it the tangential acceleration. So when you step on the gas pedal, right, you are changing the tangential acceleration. Okay, you are trying to speed up the car. But the radial acceleration comes from the fact that you are turning. The moment you turn your steering wheel, you have radial acceleration. Okay, so there are two different components of acceleration. So in general, for any motion, when there's a change in direction and magnitude of velocity, the acceleration will be the sum of that two accelerations that I've just said. So one is tangential, one is radial. The vector, they are vectors. So radial is a vector, tangential acceleration is also a vector. The resultant, right, will just be a vector sum of it. So let's say you are moving like that. Let's say this is the path that you are taking. You are driving like this. So at this point, you are turning left, correct? You are turning left. Then you can imagine imaginary circle. So you are like moving in this circular motion. Okay, so you are moving in this circular motion with a certain radius. If you are accelerating also, you will also have a tangential acceleration going in the direction that you are driving. Okay, this radial acceleration points towards the imaginary circle. So that's just one point. Later, when you try to turn right, same thing. You try to turn right, there will be an imaginary circle, right? The radial acceleration comes from the fact that you are turning, you are going into a circular motion. That's why you have the radial acceleration. But if you are speeding up, there will be a tangential acceleration here. So it's just adding them up as vectors. That will be your resultant acceleration. So remember, we talked about radius of curvature. If a curved path can be described using y equals to fx, that means y equals to something with x inside. That's a function of x. Then the radius of the curvature of the function is given by this complex formula here, this weird formula. So rho also means radius of curvature. This formula is given in your formula sheet. Okay, so dy dx is differentiate one time. So d2y dx squared is differentiate two times. Okay, so if you need, then the equation is given in the formula sheet. Okay, so for example, you have this equation here. You will differentiate one time, because in order to use that, you differentiate one time, so you can put into dy dx. You differentiate another time, so you can put into the d2y dx square, which is at the bottom. Right? When you put in, this is the radius of curvature that we are looking at. This is just for example, for example. Another question for you all to think about. Which of the following best illustrates the acceleration of a pendulum at points A through E? So imagine a pendulum. A is here, B, C, D, E, right? So A through E, that means from A, you'll go to E, then you'll come back. Okay, pendulum, basically, it will swing like that. It will swing like that, okay? Pendulum. So which best illustrates the acceleration at each of these points? Remember, acceleration is the resultant acceleration of tangential and radial. Whole thing is 1, 2, 3, 4, 1, 5. Also got people think it's 5. So the next slide, you can see which one is the answer, okay? So the answer is 5. Okay, because it's the resultant acceleration. For a pendulum hanging like this, right? It is not just moving in circular motion, it is also accelerating forward or slowing down forward in the tangential direction, depending on which point it is at. Okay, so if you take a look at the ends, right, it's either here or here. You see the acceleration is pointing tangentially only. Correct? V is the velocity. At the end, of course, velocity becomes nothing. And at the end where it becomes nothing, right, the acceleration only points tangentially. So you see down here, you point tangentially. If you go to the other side, you see the A also point tangentially. Okay, because it is not moving, then it wants to move down. When it's not moving, right, that means it's not going in any circular motion at that time. Because remember, the radial acceleration formula is v squared over r, correct? If v is 0, at that point where it's not moving, right, it's trying to turn, right, there will be no radial acceleration because v is 0. That part okay, right? Then if you look at another interesting point, which is at the bottom here, right, as it passes through the bottom, when it passes through the bottom, it is currently moving, correct? So you are moving in circular motion. Okay, but then at that point, is it trying to slow down or speed up? Nothing, right? It is not trying to slow down or speed up, right? Because just nice is in the middle. It just accelerated and then it's going to transit to decelerating, but that point got nothing. Okay, that's why you see at that point, the acceleration, right, only points to the middle of the circle. Because tangential acceleration got nothing. You are only left with radial acceleration. Okay? Okay, good. Okay, one example on this radial acceleration. A car whose speed is increasing at a rate of 0.6 meters per second square travels along a circular road of radius 20 meters. When the instantaneous speed of the car is 4 meters per second, find the tangential acceleration component, the centripetal acceleration component, and the magnitude and direction of the total acceleration, which is the resultant acceleration. So part A, right, find the tangential acceleration is actually down here. They already give you the answer already. So it's to test your understanding of what is actually a tangential acceleration. Tangential acceleration is the one that is trying to speed up your car or slow it down. Okay, they tell you the speed is already increasing at this rate. So this is your tangential acceleration. Then part B, find the centripetal acceleration. Centripetal acceleration is given by v squared over r. Okay, the speed at that point where we are talking about, they tell you is 4 meters per second. Then they also tell you the radius is 20 meters. So you can put into the formula and then you will get a radial acceleration, which is the centripetal acceleration. Okay, then for the last part, they are just asking you to find the resultant. So they are vectors, correct? 1 point here, 1 point here. So the resultant, you expect it to be somewhere in the middle. Okay, it will be somewhere in the middle. So to find the magnitude of it, you will do a Pythagoras theorem. Pythagoras theorem is the a squared plus b squared equals to c squared, that one. Okay, so from that, you find the magnitude. That will be 1 meters per second square. Then for the direction, if you take from this angle, right, you will be able to find the direction. Basically using trigo, using trigo. Depends on your reference, your angle may not be the same. Okay, this solution take reference from this outside to the inside. Let's say if you define theta to be the small angle, then of course your theta will be different. But you will know the direction exactly where it's pointing to. Okay, so this is how it works. Actually, it's quite a standard kind of acceleration we have when we are in cars or trains. So let's say you are in a car, you are turning left, or the bus is going left, right? And then at the same time, you are also accelerating. When you accelerate, you will feel that you want to fly backwards, correct? When you turn to the left, you will feel that you want to fly outwards. Correct? So in the sense, your body will feel that you want to fly this direction. Correct? This is the feeling that we get. This is the feeling. Okay, but acceleration wise is pointing here. Whatever we feel, always go in the opposite direction of the acceleration. You accelerate front, you feel you want to stay at the back. Okay. So this is curvilinear motion using polar coordinates. So location of point P described using polar coordinates. So let's say you have a point P, you are going in this path, and then you define the origin, right, to be somewhere else, okay, as some reference. So with this reference, right, if you describe this point from the reference, you are going to get R. Remember, R describes the point, right, and then some theta. So with R and theta, it describes where the point is. So if we write v theta, we are referring to the velocity in this direction, okay, which is perpendicular to R. If we write VR, we are referring to the direction that is continuing in the same path as this R. Okay, one is the radial coordinate in the same direction as the radius. The other one is a transverse coordinate. This is just by definition, So we are setting like new axis like that. Okay, it's just definition. So with these new polar coordinates, these will be the formulas that you can use. Okay, for this, if you have point P and you have a reference that is at a random place, this will be the equation that's valid. Not required to know the derivation. Not required to know the derivation. Okay, if you see a dot on top, like R dot, right, means differentiation. Differentiate one time. If you see two dots, means differentiate two times. Okay, so it's another way of writing differentiation. That's why you see dr over dt means r dot. And same thing, same kind of axis, just now is velocity, right? Now, for the acceleration, these are the formulas that you can use. And just now those in 2D, right? If it's in 3D, it's going to look very complex. Like this, let's say you have a path down here, and it really is in 3D. So this is the z-axis. Just now we are talking about plane just now, right? So plane is the one shaded in blue. So you have a r described by some angle. That's plane. Then if we have 3D, right, remember we say it's cylindrical coordinates because the whole thing, right, look like a cylindrical. Okay, look like a cylinder. You have r, then you have a theta angle here. Then you also go and bring it upwards. The whole thing look like a cylinder. So it's cylindrical coordinates. In cylindrical coordinates, then these equations will apply if you all need to use that. Okay. If circular motion is okay, then we move on to the last part of these notes. Relative velocity. Okay, okay, a bit tired already, right? Friday night, stay until 10 already. Our friends all go party, but you are here listening to me. So sorry, we still got 5 more sessions. Okay, but first 2 to 3, maybe we do a bit more until 10 plus. Then if we are ahead, right, then the last few sessions confirm can stop earlier, okay? Okay, now we come to relative velocity. So literally, right, relative velocity is the velocity of an object A with respect to another object B. Okay, relative to one to another thing. So every object can be a frame of reference with a coordinate system and a time scale. So every object that is around us, right, we also can put a frame and a time scale to it. Sounds a bit abstract, okay, but for relative velocity, that's one way to look at things. Let's say I have a XY frame on me. Let's say you have an XY frame, you have an XY frame. We are moving, right? So when we are moving, we will have some X or Y value away from each other. And we will have some velocity that is described based on each other also. Okay, so these are relative velocity. Suppose we have 3 objects shown in the image. We have this A, which is the cyclist. P is the passenger, which is in the train. A is a cyclist who is not moving outside. Okay, then B is the train itself. So A cyclist, B is the train, P is the passenger. For notation, right, this is how we notate relative velocity or relative displacement or relative acceleration, all same thing. So this is how we notate. The position P relative to B, right, will be written like this. X is the position. Then below you write P slash B. It's P relative to B. Okay, so the relationship, right, is actually given by this. We start with 1D first, which is this image not very well illustrated. 1D means straight line, right? So you imagine this cyclist is behind the train. Just imagine this cyclist is behind the train. So you have train, passenger, and cyclist behind the train. They are all in one line. The displacement relationship is given by this formula. This is how we do relative position. Okay, so PA, that means P relative to A, P relative to something that's not moving is equals to P relative to B plus B relative to A. Later, you see one example, it will be clearer. Okay, but this is the formula. So this is the position, right? Velocity, you will just have to differentiate to get the velocity, which very nicely, it also ends up with the same thing. Okay, so VPA, you see is PA is the same. Then down here is PB. This dash X is just trying to say in the X direction. You can also ignore because we are talking about 1D only. Okay, dash X, that means in the X direction. Behind is BA. So you see velocity and the position is the same because you just differentiate. So, okay, this is the simple example. If P relative to B is positive 1 meters per second, that means P relative to the train, you are moving 1 meters per second inside the train. You are walking 1 meters per second, or rather you think you are walking 1 meters per second. Then B relative to A, right, is the train is moving 3 meters per second with respect to something that's outside that is not moving. So the actual speed of the train is 3 meters per second. Then the passenger is inside the train moving at 1, or she thinks she's moving at 1. Then the velocity of the passenger relative to a stationary object outside, right, the real velocity, is actually this one plus this one. Remember, VPA equals to PB plus BA, correct? In the previous slide. So you take 1 plus 3, it will become 4. So the passenger thinks she's walking at 1, but actually she's moving at 4 because the train is also moving. Okay, so 1D is easier to understand. This part, you all can understand. Okay, this part, so this is relative velocity and relative position, all that, right? Now is the basic. So try to understand on the basic, because when we reach the end of the course, right, we will be talking about mechanics of machines. We'll be looking at things like, machine moving part. Let's say you have this part, okay, this part joining to another part, which is joined to another part. Then when this part move, right, the other part will move with this part. Then in turn, the other part will move with the second part. So if you just drive this thing around, right, you can imagine the whole machine moving. So there will be relative velocity of this point at the end of the third part relative to this point. You also must know how to calculate that. So that's relative velocity. And then same thing, like relative acceleration of that point relative to this, or whichever the question is asking. So for mechanics of machine, right, when we look at a lot of moving parts together, this relative position, velocity, and acceleration topic will be quite important. If not, it will get quite confusing. It will get quite confusing. If you can visualize all this, right, when you reach that topic, it will be easier for you all to understand. In this course, towards the end, we have a sort of some intro to mechanics of machine. Then throughout this entire course, right, this RMIT course, you have another dedicated module, I believe, for mechanics of machine also. That one will be doing a lot of all this relative stuff. Okay, so all this is to build up your knowledge to reach the understanding of mechanics of machines. Okay, so the right here, this is the frames that we are talking about. Everything we can plant a frame, right? We can plant a frame on it. So this one is a cyclist frame, which is not moving. Then this frame here, you see this frame Y and this X, right? This is the velocity of the train. So you can imagine this frame, right, is moving on the other frame. So this frame is not moving. This black one is not moving. Then this frame is moving forward. So later on the frame will look like that. After some time, the frame will continue looking like that. Then after that, it will look like that. Okay, so the frame is moving away. Okay, that's why we say every can have a frame on it, and then the frame can move one. So if we think of this relative velocity in terms of frames, right, it will look like this. And then the position of passenger, right, will be at some point. So you can see from this, don't care about the one I draw. Don't care about the one I draw. If you care about this point P, right, if you see it from the train's frame, it's only quite short, right? Together with the train, only a short distance away. But if you compare P to the cyclist frame, is much longer path away, correct? So this is the frames that we are talking about. Okay, so that's in 1D. After we learn 1D, we go to 2D, 3D. Actually, the formula is the same. Just now we use X, right? Now we use R. R stands for position vector. So you realize the bottom here is all the same. Okay, PA equals to PB plus BA. And same thing for velocity also like that. So just now, okay, this illustration, right, is better for 2D. 2D, that means they are on a plane. So cyclist is outside, the train is moving in this direction, then passenger is moving in another direction, perpendicular to the train at 1 meters per second. So if you go and want to find the relative velocities, right, all these will become vectors. Okay, this is a vector and this is also a vector. So we imagine this coming down one is the VBA, that means train relative to cyclist is moving down 3 meters per second. And the passenger relative to train, she thinks she's going to the right, all right, relative to the train, she's going to the right at 1 meters per second. So this VPA, that means P relative to outside, this is her actual velocity. So in actual case, right, she's moving in a direction that is pointing down and to the right, because the train is moving down also, and then she's moving to the right. Okay, so this is a true velocity. And to calculate the value, right, why is it 3.2? This one you will use Pythagoras theorem. Okay, so you use Pythagoras theorem to calculate 3.2. For angle, same thing, you will use trigo. You will use trigo to calculate. Okay, let's go through example. I think, yeah, just these two examples, then we can end class already. Okay? No. Go through assignments first. Very short only, also very short. Okay, flying in a crosswind. The compass of an airplane indicates that it is headed due north, and its airspeed indicator shows that it is moving through the air at 240 kilometers per hour. If there's a wind of 100 kilometers per hour from west to east, what is the velocity of airplane relative to Earth? So if you draw it out on a diagram, it will be like this, traveling upwards, right? Due north at 240. There is also a wind going 100 to the east. So PA is plane relative to air. Then this one is air relative to Earth. Okay, then to find the velocity of the airplane relative to Earth, that means the actual velocity is actually this one. Okay, VPE equals to VPA plus VAE. So that's how you get this line. Okay, so now you draw this diagram already, right? You just need to use your Pythagoras theorem and your trigo to find the actual direction. The pilot thinks he's moving upwards, but actually he's moving a bit to the right also, okay? Because there's wind blowing. Any questions? Don't have, right? Okay, good. Then we continue. Actually, it's the same example. So continue from previous example. In what direction should the pilot head to travel due north? So just now she fly upwards, right? She go a bit to the right, but she actually want to fly upwards, right? If not, she'll end up different place, correct? So she want to fly upwards. So what will be her velocity relative to the Earth? The airplane speed and the velocity of the wind are the same as in previous example. So the wind is still traveling to the right. You want the resultant to actually really be upwards. So you can expect she needs to fly the plane upwards and to the left, right? So she fly upwards to the left, then plus the wind blow it to the right, it will end up like this. But what is the value that is actually needed? You will draw this diagram, then you will calculate. Okay, so her plane is still going at 240 kilometers per hour with relative to the air. Okay, don't care where the air is blowing, but it's going at this speed. So this is 240, this is 100. From here, you will same thing, use Pythagoras theorem to calculate. You get 218. There's something wrong with the units. Not supposed to have a square here. Okay, so 218 kilometers per hour. Then the angle, same thing, you will use trigo to calculate. Okay, so in an actual scenario where plane is like that, right, of course you waste fuel. You see you fly 240, right? Actually the wind is blowing slightly, push you back. So in the end, going a bit slower. Okay, any questions? Then from here, it's all supplementary questions for you all to take a look. If you all got any questions, can kind of ask me. Okay, then I think I will just take about 5 minutes, 3 to 5 minutes to show your assignment 1 and assignment 2. Won't take so long because I cannot teach you how to do. It's you are marked, right? You are assessed anyway. Yeah, so let me just show you. Yeah, I need to share screen with the online people. Okay, can see, can see, So this is your assignment 1 and you'll be worth 20%. So basically you will follow the instructions that are already written here. So it should be in the form of a report, which will include cover sheets, layout, formats, and references. So references are for, like, let's say you refer to something online or refer to any resources. You all need to cite. You all need to cite. If you all learn how to do from online, just cite also. It's a proper report. So it should have an introduction, results and discussion, conclusion, and recommendation section. Okay, and it will be marked. All of these will be marked. So it should be typed and then submit a PDF. So you see down here, right? Of course, by today's lesson, you will know a lot of the concepts. But you see down here, they ask you to solve using analytical methods and also working model simulation. But I don't require you all to use the working model simulation. Okay, so I reduce your workload. So you all only need to use the analytical methods. Analytical means you all really do out the equations, solve it like how you all will solve in the exams. So whatever we have learned so far, right, they are analytical. Simulation is like using software and then let it run and find the results. Those finite element analysis, all those is simulation. So we are not doing those, and I don't require you all to do those. Okay, don't require. Okay, so you will have a question, something like this. This is a pulley. You all will know how to do this after today. Of course, maybe some of you will know, but we haven't covered it. All these forces and stuff. So they ask you in 2 ways, find whatever you need to find. You use force and acceleration method. Then you also use another called the work and energy principle method. You all would know. So these are 2 methods. And then also they ask you to use force and acceleration methods, use the impulse and momentum principle to find. So on top of this, right, actually must use the simulation, but I don't require you all to use the simulation. Okay, don't require you all to use. Because I know all of you probably working and all have a lot of work also. So don't need to do the stuff that won't be tested. And same thing for the other part. Okay, it's just a question and then you'll write out the solution and then submit the whole thing as a PDF, which will mark and then give a score to it. Okay, we'll mark and give a score to it. And then these assignments, I will not guide you all how to do because it's assessed. So 20%. Imagine you ask me how to do, right? I tell you, you get the mark, but then the rest don't get, cannot, right? So all this I cannot guide you all how to do because it's assessed. But the notes and the supplementary questions, right? All the other stuff, like y'all can come and ask me. After class or email also can. Okay, I'll be happy to answer, just not the assignments. Okay, so this is assignment 1. Any questions for assignment 1? Then for assignment 2, right? Assignment 2, okay, this is assignment 2. It's due at a very late date. By the time, it's already after my last lecture with you all sometime already. So I will be taking 6 lectures, and then a lecturer from RMIT will fly in here to take another 3 sessions. So I'm taking the lecture part, right? I'll teach you all this lecture stuff. Then she will be doing the tutorial solutions with you all. Okay, she'll be doing the tutorial solutions. The concepts are the same, but sometimes, the notation may not be the same. Notation may not be the same. Remember, I say maybe the radius of curvature, some people use R, some people use rho, this kind of thing. It may not be the same, but the concepts, they are all the same. Okay, and okay, so this is assignment 2. Basically, also just follow all these instructions. Report should be about 12 to 15 pages, excluding all the cover page, content page, list of figures, and list of tables. So this is a very freestyle kind of assignment. I purposely choose this, right, to give you all marks. Because when you all do questions, right, if you all get wrong means wrong, I cannot give you all marks. This kind of freestyle, right, if you all put in effort, right, I can give you all the marks. I can justify to give you all the marks. So it's to help you all. Okay, so basically you just choose a movie or game that you are familiar with, then discuss any engineering concepts within. Of course, the topics that we have learned, that means the physics that we have learned. So these are guidelines which you may or may not follow. I say may not, so is to make it even more freestyle. Because if I put may follow, right, it means everyone will follow. Of course, you can follow, then if you follow, confirm won't go wrong. If you want to, go big or go home kind, then may not follow, but better be better than all this. Okay, so standard, you introduce and describe the movie. You assume that the reader does not know the movie. So maybe first 2 page describe. You can have screenshot to describe what the movie is about. Then after that, the whole report behind, right, it should be about you take certain scenarios in the movie to talk about the concepts inside. Now, today we only learn velocity and acceleration. Next time we will learn momentum, force, all this, right? For example, let's say Thor, the hammer, right? You will pull up the hammer. Why one can pull up, the other guy cannot pull up? Does it make sense or not? Maybe you draw we will learn this thing called the free body diagram, which is for forces. You draw that out, you assume values, you calculate whether it makes sense or not, then you can briefly describe. Okay, so basically relate what you learn in class to something real, like a movie, whether it's nonsense or not. And then if it's so nonsense, right, why is it? Maybe you can talk a bit about why is it designed that way. Maybe it's for comedy effect, maybe. Or for games, right, why is it so simplistic? Maybe it's for low spec phones, for example. Just saying only. But all this stuff, right, is not as important as showing your knowledge. So the part where you draw diagrams, you put values, do equations, calculate the values, all this knowledge, right, those will be marked more heavily. Okay? Those will be marked more heavily. And yeah, so this is quite a freestyle kind of report. If you put in effort and don't write the wrong thing, right, you will get the marks. Wrong thing meaning, let's say some people, they want to calculate the motion. Today we learn motion, right? You want to calculate, you got this thing fly over, you want to calculate the velocity at that point. Then you say the acceleration is changing, but you go and use the kinematic equations. You know what the mistake is? The equation is for constant acceleration, but the student say the thing is increasing in speed, is accelerating, but you still use the equation. This kind of thing becomes a wrong concept. So that one we have to minus mark. But in general, very hard to minus marks on, okay? Because it's very freestyle. Just put in effort to do this. Yeah, so that should be all for today's lecture. Any questions? All solo. All solo, but actually it won't be so long one because you think about it, you will have figures. You will need figures to explain what you want to illustrate. But of course, the figure don't want figure one page then your content won't have enough. Okay, if your figure take up 1/3 of a page, like this, okay Okay, then maybe in our whole report got about 6-7 figures. That's fine. Okay, any other questions? If no questions for now, also okay lah. Along the road, you have questions, can come and ask me again. Okay, so today we'll end class here. Yeah, those haven't marked attendance yet, remember to mark. Okay. Okay, thanks everyone for attending. Thank you.